So where do we begin? Well, the basic idea is that we can think of any function as a series. In fact, this really started right at the very beginning in our calculus journey, almost the first day, where we said, you know, in Calc 1, we have this idea that f of x is kind of like the tangent line. Well, kind of like there's an error term, but nearby, the function looks like a line. That's sort of the very first thing we learned. And in Calc 2, we said, you know what, we can do better. So when you think about what a line is doing, it's using just a little bit of information about the function, namely the value of the function and the value of the derivative. Calc 2 says, well, let's push it a little bit. What if, for instance, we used information about the second derivative and we get a better approximation? And this was called the Taylor polynomial. Now, if you're looking closely, you might notice like, oh, our error has gotten smaller. The more information that you're using, the better your approximation, the smaller your error is. And so they said, all right, well, let's use all the information. What does that mean? Well, it just says you keep adding more and more terms, more and more information about local behavior from the derivative. And instead of dealing with what we call Taylor polynomials, you get what are called Taylor series. And we get that sometimes, not all the time, but sometimes. The function is indeed this big infinite polynomial. Okay, so that's the idea. It's like, okay, so we can think of functions as these big polynomials. So when we use the word series, that just says we keep going all the way up to infinity. So, but if it helps in your mind, just say series are polynomials. Okay. Well, in Calc 2, what did we do? Well, we would start with a function. Say, here's this function e to the x, or cosine of x, or whatever function it had to be. We say, look, we know what the function is. Now let's find the Taylor series. Okay, well, what are we going to do? The thing is, we don't know what the function is. We're after a function. What is the function we're after? Well, we're trying to solve differential equations. It's kind of the name of the class. And we're saying, okay, well, in that case, we're going to start with the solution to our differential equation, which we don't know what it is, but then we're going to figure out a good approximation to it by figuring out, well, what does this polynomial look like? So that's the idea. That's the idea. So our goal here is to say we want to understand functions which we're having a hard time solving. And then we say, well, every function looks like a polynomial. Let's figure out that polynomial. And so that's our goal. So a couple of basic ideas that we'll mention here. Yeah, we've already said a few things out loud. So a power series is an infinite polynomial. And so really, we have all these C0, C1x, C2x squared. And what's our goal? Well, our real goal is going to be find these coefficients. What are they? If we knew what these values are, then we have a good approximation. And indeed, if we knew all the values, then we might have the entire function. Now, there's various questions about convergence, and what does that mean? And the idea is that series converge when the partial sums converge. We won't get too much into that. We will talk a little bit about radius of convergence as we go on. But the important idea says, all right, and we're going to use this. Two series, so think again, if you like, two polynomials, are equal if and only if their coefficients are equal. Now this shouldn't surprise us, because we used it for partial fractions. We said, hey, we can use this to figure out what those constants are for partial fractions. We would look at what the coefficients are and match things up, and then that would tell us information about what the values should be. We're actually going to do something very similar to that. We're going to say, I have this one big polynomial, and I have this other polynomial. Usually it's 0, doesn't have to be. And then I'm going to compare the coefficients of these polynomials, and that's going to help me find these various c sub I. All right, so now a very intimidating page, but I don't want you to be too intimidated. It'll look like a wall of text, but let's just talk about the important parts. So the thing is, we want to be able to work with power series. Now, when it comes to power series, there's really only two series that we want you to be really comfortable with. And it's these first two which are listed here. So the first one, 1 over 1 minus x, is the sum 0 to infinity of x to the k. This is called the geometric series. And the other one is e to the x, which is the sum k equals 0 to infinity x to the k over k factorial. Now, we want you to know these really well. How well do we want you to know these? Well, how do you know we want you to know these? I boxed it, yes. Where else have you seen these? These are on the formula sheet. They've been there all semester. Ah, so now we know why they're there. They're there because we were coming for them. Now, what about the rest? Well, I'll be honest with you. I don't expect you to know these by heart. And if you need them, we'll give it to you. If you don't need them, well, we won't give it to you. I should make a couple of comments here. For a geometric series, by the way, do you know why we call it geometric? Do you remember that? Well, so geometric here means multiplying. So you might think of, there's sort of two ideas, arithmetic and geometric. Arithmetic means adding. Geometric means multiplying. And what happens is, if you look at this, you get 1, and the next term is x. The next term is x squared. The next term is x cubed. So what you're doing is every time you're multiplying by an x. And that's why it's called geometric. It deals with multiplication. All right. So, walk down memory lane. When does a geometric series converge? Do you remember that part? Yeah. This converges as long as what you're adding up is small. Now this other function, this exponential function, e to the x, sum from 0 to infinity x to k over k factorial, when does this converge? Do you remember that one? I know, Calc 2 was a long time ago. For all x. No matter what x you pick in, it always converges. In some sense, this is why we say that factorials are much bigger than exponentials. All right. So that's the left side, but I'll be honest with you, the main thing is this right-hand side. This is where all the action is at. And so you will either succeed or fail in this part of the course, depending upon how well you can do what's listed here. And that is to say, we want to work with these series, and so we want to be able to do things to them. And so the first thing here is to say, well, we want to put things together. So it's like I have two series, and I put them into one. And it says, okay, can we do that? And it says, well, yeah, you can do it. Now, there's some subtleties here. I want to point out some subtleties here. The first subtlety is you have to make sure that the starts agree. If the starts don't agree, hopeless. All right, well, you might say, well, what happens if we don't have that? We'll get to that. Now, the other thing that you want to make sure of is that these exponents all agree. And so that's the other thing. So the starts agree, and then these exponents agree. And once we have that, we put everything together and compare coefficients, and life is good. Life is wonderful. Okay. So, and I'll tell you, that's basically the name of the game, is how do we put series all together into one part. Okay, so what are some things we can do? Well, if we want our starts to agree, one thing we can do is we can say, well, we can pull off some terms at the beginning. So maybe one series starts at 2 and the other series starts at 5, so that's no problem. We'll take the series that starts at 2 and just pull off the first 3 terms, which is what we're saying here, pull off the first couple of terms, and then we start the rest of it. So you can pull things off. So that helps fix the starts agree. Now, the more important thing is, okay, well, how do you make exponents agree? And for that, we want to be able to shift our index. And it's really substitution. And I know you might be thinking, substitution, that sounds like something from calculus. It's the same idea. You see, substitution is, at the end of the day, it's about changing the name. I have one thing, I'm going to call it something else. And in the process of doing that, I'll have something which is easier to work with. That's what substitution is, changing names to make things easier to work with. So how does it work? Well, you say, okay, let's look at the sum. I have ckx to k minus I. So I say, all right, my care is the exponent, because that's what I want to make sure things line up. And so I say, all right, what I want to do is I want to change my name. So I'm going to change my name by taking this k minus I and calling it my new thing. See that, how I even wrote it there? So I'm going to rename what I have. Of course, this is the same as saying k equals L plus I. Now the key here, think back to substitution in calculus. You have to change every single occurrence. So I'm going to change my exponent, but I also look and I say, well, where else does a k show up? And it shows up in the coefficient, and it shows up in this sum. It even shows up a little bit up here, because when we say to infinity, it really says k to infinity. And now we say, all right, so originally I'm summing over k. I'm now switching to L. It's my new variable for my sum. So if I want to figure out where do I start, well, if k was m, L is m minus I. I use the relationship. If I'm going to infinity, if k goes to infinity, L goes to infinity. So it's still infinity. This c sub k, well, k is L plus I. So it's update every k. So if you just think of it like substitution, life is good. The other thing we'll need is how to take derivatives of power series. And the answer is you do it in the obvious way, which is to say, when you're taking a derivative, you take it term by term. So if I have my sum, ckx to k, well, I still have a ck, derivative of x to the k comes down, x to the power k minus 1. All right. And the last thing, which we won't use too often, but might from time to time, is multiplying series. So I have two series. I want to multiply them together. And that produces a new series. So I have the sum akx to the k, sum bkx to the k, and that's a sum where I have this new series, sum ckx to the k. And what does the ck look like? Well, there's this formula. And you might notice there's a familiar word. We recently talked about convolution. If you remember convolution, that was, when we talked about it, that was the integral from 0 to t, f of tau, g of t minus tau. That's what we called convolution before. But what's the key? In one function, we're going up from 0 up to t. The other function, t minus tau, we're starting at t and going down to 0. So they go in the opposite directions. That's what it means by convolution. And I think in this case, it's a little bit easier to see what's going on when we talk about this multiplication. So let's look at that for just a second. So if I'm going to multiply two polynomials together, well, it's always the same tool. You FOIL. Now, doesn't really literally mean first, outer, inner, last because, well, there's a lot of terms. So how do you multiply two big polynomials like this? What's the basic philosophy? Yeah, you got to pick something from here. You got to pick something from there. And you multiply it, and you do it in every possible way. All right. Now, what's one way to think about it? Well, one way to think about it is I'm going to start with one polynomial, and I'm going to write the other one, but I'm just going to write it in reverse order. Now, suppose I wanted my constant terms. How can I form a constant term? Well, the answer is the only way to get a constant out of multiplying is to multiply the constants together. So that's A0, B0. No big surprise. What if I wanted to get an x term? Well, we can shift and say, look, the only way to get an x term is A0, B1x, and A1x, B0. So you'll see I'm going in one direction for the other, and the opposite in the other. Again, we could just slide along. If I wanted an x squared, A0, B2, A1, B1, A2, B0. And so that's sort of where convolution is coming from. This notion, we're just sort of moving them along and they go in the opposite direction. All right, so that's that philosophy. Okay, so let's try an example. Rewrite the following as a single power series. All right, so we want one series to rule them all, one series to find them. Okay, so what's the general philosophy? Well, here's my approach. When I'm looking at a problem like this where it says combine things, write things as a single series, in the back of my mind, I say step one, I want everything to have the same x to the L. I want all my series to look like this. So that says the first thing I worry about is taking care of any shifting of indices. Then the second thing I look at, after I've gotten that taken care of, is I check that the starts are the same. And then the third thing is I put it all together. So at the end, there's really just sort of three basic ideas. Making sure the powers all line up, making sure the starts all line up, and then put everything into one big sum, and then life is good. Okay, so we start and say, all right, are the powers the same? No. No. Okay, so we're going to do some reindexing. Okay, so step one, we're into our reindexing. So here, I have k minus 2, so I'm just going to make a substitution, L equals k minus 2. Here I have k plus 1, so I'm going to do a substitution on this one, L equals k plus 1, different substitution for the different series. That's okay, I can treat them separately. All right. So let's work on the first series. So in the first series, L equals k minus 2, we could also, by the way, write this as k is equal to L plus 2. Let's talk about what happens to our sum. We start at k equals 2. Where will L start? 0, right? 2 minus 2, 0. Where will it go to? It goes to infinity. It's really hard to change that infinity. Okay, what happens to this k times k minus 1 times ck? Well, just term by term. What happens to this k? L plus 2. What happens to this k minus 1? You can think of it as L plus 2 minus 1. And of course, we can work that out. That's L plus 1. What happens to this c sub k? C L plus 2. And what happens to the x to the k minus 2? X to the L. Okay, good. Now our first sum is in terms of our L. Okay, so we'll switch and work on our second sum, plus k. So this is k is L minus 1. We have the sum. Where does L start? 1. And we go to infinity. Okay, what happens to that coefficient? C sub k? Cl minus 1. X to the k plus 1 becomes x to the L. All right. Now I'm happy that everything looks like x to the L. So this is going to let me pull things together. And the key is, why do I want things to have the same x to the L? Because I want to group coefficients. That's what's really happening. I'm setting myself up to group coefficients. And so here I'm just making sure that these match up so that I can group very readily. Now I go to the second thing and say, well, are my starts the same? No, they're not. Okay, so we need to fix that. Well, what do we need to fix? Between the two, do we need to fix this first sum or the second sum? Yeah, the first one. Essentially, we want the start to be the largest one among them. So we're going to start at 1, is where we want the sum to start. So the thing is, we're going to say, okay, we need to pull off terms. Now in this case, how many terms do we need to pull off? Well, I need to pull off 1 term. So how does it work? Well, imagine you put in L equals 0. So if I put in L equals 0, this would be 0 plus 2, 0 plus 1, c sub 0 plus 2, x to the 0. So I'm making this very explicit here. This is L equals 0. Plus, the next term would be the 1 term. But now I say, well, hey, that's 1 as well. So I'm just going to put all the remaining terms into the sum. So L plus 2, L plus 1, CL plus 2, x to the L. Now on the second sum, what do I do? Just leave it as is. All right. So, when it comes to the sums, are these ready to be put together? X to the L's match, the starts match, I'm ready to go. Those are the two things I have to check. So I still have this term in the front. So that becomes 2c sub 2 plus the sum L equals 1 to infinity of, and because these both have x to the L, I can pull it out, L plus 2, L plus 1, CL plus 2, plus CL minus 1, x to the L. And now what? Yeah, that's it. Box it. Now when it comes to this last week of the course, this is the hard stuff. If you can get through this, you're in good shape. Any questions? All right. Well, in that case, you should practice getting through this. Rewrite the following as a single power series. Sum k equals 1 to infinity, 5k c sub k x to the power of k minus 1 minus the sum k equals 0 to infinity 2c sub k 1 plus x squared times x to the k. Okay, so what's our great challenge here? How do you handle this 1 plus x squared? Split it up. And they're like, how could one possibly split it up? Well, it's called, you expand on the inside, right? So this is the same as this sum. We have our first sum, 5k ck x to the k minus 1. Then minus, and we'll just grab just the first one, just the one. So that's the sum k equals 0 to infinity 2ck x to the k. And now grab the x squared term, and that's a separate sum. K equals 0 to infinity 2ck x to the k plus 2. That's our great aha. So in other words, the same thing that allows us to push sums together allows us to pull sums apart. Okay, now, what happens next? Yeah, we have to compare, right? Are we ready to push things together? Well, our exponents say no, we're not ready yet. So what's the substitutions that we make? On the first sum, what do we substitute? So L equals k minus 1 here. L equals k here. Okay. So, all right. That's the substitutions. And we carry out the substitutions. And we get that. So that's what we translate to, those sums. So the sum from 0 to infinity, 5 times L plus 1 times C sub L plus 1 x to the L, minus the sum from 0 to infinity, 2c sub L x to the L, which actually is very easy to just copy, minus the sum from 2 to infinity, 2cl minus 2x to the L. Now you might say, did we really have to change this? I like to just make sure all my things look the same. Okay, everything looks like x to the L. By the way, there's nothing special about L. It's just the letter of the alphabet that came after K. So don't get too caught up on like, oh, it's a J. What am I going to do? It's a letter. You'll survive. Are we ready to push these together? What's wrong? Got to pull terms off. Where do we need to pull terms off of? How many terms do we have to pull off the first one? 0 and 1, right? Because we got to get, our common start will have to be 2. So we're going to pull 0, 1 off here, and 0, 1 off here. All right. So when we pull off 0, we can just plug in 0. We get 5 times 1 times C1. Here we get 2C0. So that's our constant term of our series. So this is the coefficient of x0, our constant term. When we want our coefficient for x, well, that's plugging in 1. So 5 times 2 gives 10, C2 minus 2C1, x. And then everything else is one big sum, starting from 2 to infinity, and you just put them all together. Pull out the xCl that's common, so you have the 5 times L plus 1, CL plus 1. You get the minus, don't forget the minus, 2CL, and the minus 2CL minus 2. All right. There we go. Okay. Got it? This is the name of the game for this week.
Why do we have to split it?
Why do we have to split up here at the start? Because otherwise, why would we say, aha? Oh, wait, no. No. What's the goal? So I think the answer to your question is, well, you're asking the question, why do we expand out and split? And the answer is to understand what's our long-term goal. Our long-term goal is we're grouping coefficients with the same power. That's our goal. So that's what's happening at the bottom. This x to the L, what we've done down here is we said, this is our constant term, here's our coefficient of x. If I want my coefficient of x squared, I plug in L equals 2. If I want my coefficient of x cubed, I plug in L equals 3. Coefficient for 100, plug in L equals 100. So why did we split? Well, the reason why we split is I need to have all my powers be the same. And so when I have this polynomial term in here, I say, wait, that's not going to work out well. That's not going to mesh with the idea of grouping coefficients. So I multiply out. So I have x to k plus 2, because I want to separate them so I can re-index that k plus 2. So then I can push them back together. It's sort of this idea of I'm pulling them apart. I'm going to modify them. So then I can put them back together, but they all have the same power. So that's the idea. All right. Well, that was sort of half of what we're going to do. There is a second half. So let's go to saying, all right, what does this have to do with differential equations? So we'll jump to a different example. So given that y is equal to the sum 0 to infinity ck x to k is a solution to y double prime plus xy equals 0, where y of 0 equals -4 and y prime of 0 equals 3, then determine a bunch of coefficients. There's nothing special about stopping at 8, but we want to, stop at some point. So we'll go up to 8. Okay. So you might be saying, how do we do this? Well, it's actually a really simple idea. Here's the idea, where it said, this is y. So when we put on our verify hat, what do we do when we have y? We plug it in. And that is what we do. It's the same thing that we've been doing quite frequently this semester. It's like, plug it in. So what we're told is this sum, k equals 0 to infinity, ck x to the k, double prime, plus x, sum, k equals 0 to infinity of ck x to the k, is equal to 0. All right, that's what we've been told. Okay, so let's rewrite some of this. Okay, so this x I can multiply in. Yes? Okay, good. All right. And okay, let's talk about derivatives. So y, that's our sum. We'll do the derivatives here on the side. Ck x to the k. What does y prime look like? Still the sum. What happens? Think of taking the derivative of x to the k. So the k can come down. X to the power k minus 1. How about y double prime? Yeah, k times k minus 1, ck x to k minus 2. Now, on a side note, we start at 0 for our sum, but what happens when we plug in 0? We get k equals 0, goes away. What happens when we plug in 1? We get 0. So what can we do with this sum? We can start at 2. We don't have to, but we can. All right, so this first term becomes the sum k equals 2 to infinity of k times k minus 1 times c sub k x to the k minus 2. The second becomes the sum k equals 0 to infinity c sub k x to the k plus 1. Now, does that look familiar? It's like we've seen this before, this kind of thing. Or maybe we've seen this exact thing. What? Oh my gosh, it is the same thing. Wow! Okay, so we didn't know it, but we were solving differential equations back here because that's part of the step. So what do? Well, this is where we say, aha, rewrite this left-hand side. Okay, so now we're going to rewrite, and by rewrite, what we really mean is we're combining coefficients of powers of x. That's what we're really doing. I don't know why I put lowercase i's for some reason. It's very strange. All right, so here I'm going to rewrite it by just copying what we wrote. So we now have that 2 C2 plus the sum 1 to infinity of L plus 2, L plus 1, CL plus 2, plus CL minus 1, x to the L equals 0. All right. Good news. Now, a question. How do we use this to find the C's? Well, actually, they told us some C's already. But they did it very, quietly. They didn't want to draw attention to themselves. So suppose we plug in 0 into this function. What comes out? Now, one person up front said -4, but what else comes out? Well, what happens with all these zeros? They drop out, right? 0 is a friend. But one thing doesn't drop out. What doesn't drop out? C0, the constant term, doesn't drop out. So what happens when we plug in x equals 0, we get that y of 0 is equal to C0. So these initial conditions are helping us prime the pump. It tells us what C0 is. Come here to the next one. Let's plug in x equals 0 here. So we plug x equals 0 into our derivative. What comes out? Yeah, so what's the constant term now in your derivative? The C0, the constant term for your function, take the derivative, disappeared. The C1x now became your C1. It's your constant term. So, they secretly were telling us C0 and C1. Wow, we're like a fourth of the way there. We haven't even broken a sweat yet. Okay, now we go to our rest of our terms. Time for the rest of the story. This is a polynomial. This is a polynomial. I know you're like thinking, Steve, that's 0. Yes, 0 is a polynomial. It's very flexible that way. If two polynomials are the same, what are true about all the coefficients? They have to be the same. So what does that tell us about this coefficient, which is our constant coefficient? Has to be 0. What does it say about this coefficient? It has to be 0. Now this is true for L starting at 1, 2, so forth and so on. All right, given that 2C2 equals 0, what can we conclude? We can conclude C2 equals 0. More progress. I like this. We're 3/8 of the way there. Some people might say that's like 37.5%. But I like 3/8. Now, we come here. Okay, plug in L equals 1. What does this tell us? L equals 1. So I'm going to recopy this down. L plus 2, L plus 1, CL plus 2, plus CL minus 1 has to equal 0. That's the conclusion. And plug in L equals 1. We're going to get 3 times 2 times C3 plus C0 equals 0. But what do we know? C0 equals -4. So 6C3 has to equal 4, right? Because -4 comes across. So that tells us C3 is 2/3. Well, what do you think we're going to do next? Plug in L equals 2. We just work our way up. We work our way up. Constant term, coefficient of the x to 1, coefficient of x to 2, and you just keep going. Okay, we plug in L equals 2. What do we have? Upstairs? Oh, sorry, this recursion becomes 4 times 3 times C4 plus C1 equals 0. Well, what do we know about C1? It's 3. Actually, so those 3's cancel. Can you see what C4 is? 0. -1/4. All right, the 3's will cancel, which leaves us with 4C4 plus 1 equals 0. 4C4 equals -1. C4 equals -1/4. All right. I see our time is almost up. Should we do one more and call it a day? Once more. Once more. Well, what do you think the next one we should do is? Yeah, exactly. You just keep working your way up. So 5 times 4 times C5 plus C2 equals 0. But what is C2? So what is C5? 0. That seems like a really fitting place to stop, I guess. All right, so that's our idea, and we'll work on it more next time.